So to explain the purpose of the low-pass filter, what we have here is some data that I'll animate in a moment after I explain what is going on. What we have here is the spectrum of a function. The function is the cosine of pi times t plus 3/4 of cos 2 pi t plus a half of cos 3t. So you expect to see some spikes at frequencies in hertz of a half, 1, and 1.5, which are given by these three separate cosine functions, respectively. And here I've just plotted the absolute value of the Fourier transform between 0 and this frequency here, which is the Nyquist frequency I'm using to sample the data. And so if the Nyquist frequency here is 5 Hertz, then I've sampled my data correctly, and each of these frequencies here appears in the right place. Now, if we decrease the sampling rate, then the Nyquist frequency will also decrease. So let's see what happens to these peaks as we do that. Okay, so far so good. The actual frequencies are shown here with these dots, and then these peaks appear in the correct place. But something interesting is about to happen. When we get to this point here, this highest frequency is approaching the Nyquist frequency. What's going to happen? Well, as we go through the Nyquist frequency, that peak reflects off that wall and starts traveling back. Now we know that this frequency here is 1.5 Hertz, but as we decrease the sampling frequency, decrease the Nyquist frequency, it's being interpreted as all kinds of frequencies between 0 and the Nyquist frequency. So it gets wrapped back into the domain between 0 and the Nyquist frequency. If you're sampling, say in this situation here, if you're sampling at 2 Hertz and your Nyquist frequency is 1 Hertz, you just can't understand any frequencies that are higher than that. And so they don't just go away, they wrap back into your domain. So for example, with this particular sampling rate here of 1.9 Hertz and Nyquist frequency of 0.95 Hertz, we seem to be picking up a frequency here of 0.4 Hertz. But there is no 0.4 Hertz in this spectrum. It's an artifact. This is actually a peak caused by the signal at 1.5 Hertz that's been wrapped back into the domain. So this tells you something really important about collecting data and sampling it, digitizing it. If you, say, have a data collection system, let's say I've got a microphone and it's measuring frequencies up to, say, 40,000 Hertz. So your microphone is sensitive up to 40,000 Hertz, but let's say your digitization system is sampling at 20,000 Hertz. So if you're sampling at 20,000 Hertz, your Nyquist frequency is 10,000 Hertz. So every frequency that is in your audio signal, as in the signal that's traveling through the air, every signal between 10,000 Hertz and 40,000 Hertz could be wrapped back in to your data and expressed as a frequency between 0 and 10,000 Hertz, even though it's not really there, because your sampling rate is only 20,000 Hertz and your Nyquist frequency is 10,000 Hertz. The frequencies above that don't just go away, they're reinterpreted and placed somewhere between 0 and the Nyquist frequency. So to fix that, you need a low-pass filter in your data collection system. Between the signal collection point at the microphone and your digitizer, you need to put something, some sort of low-pass filter that cuts off every frequency above the Nyquist frequency. And then you won't get these artifacts. This problem is called aliasing, and it's a real problem that you've got to address if you want to collect sensible data using digitization systems. So the take-home message here is that frequencies do not go away. If you've got frequencies that exist in your signal that are above the Nyquist frequency, and this signal hits your digitizer, then you'll see that as an artifact in your data that does not actually exist. Now, the way I presented this aliasing seems a little abstract perhaps, but it's actually something you're almost certainly familiar with, assuming you've watched TV or movies. Because when you capture a movie, you're doing it at some frame rate. You're taking some vision of the universe and splitting it up into frames, typically somewhere around 30 or sometimes 60 frames per second. And because you're sampling things, sometimes you get beating and aliasing. So here's an example with a bike tire that I filmed at 60 frames per second. And there's some tread pattern here, and you ask the question, how fast are the knobs moving past this pointer that I've inserted here? The maximum speed you can see them moving past would be at the Nyquist frequency if you're sampling, And sometimes they appear to be stationary, not moving past the point at all. Sometimes they're moving to the left, sometimes they're moving to the right. You don't actually find out which direction the wheel is moving until right at the end of this video, where the wheel slows down enough that you're no longer aliasing the vision that you're capturing at this 60 frame per second rate.